Welcome to The Explainer. We all think we live in this perfect digital world, right? A world of clean ones and zeros, of flawless data streams. But underneath all that, there's a secret, a physical, kind of messy world that makes it all work. Today, we're going to pull back that curtain on the hidden life of analog engineering. So, let's start with a problem you've probably experienced without even realizing it. You plug in a high-speed cable, like a USB or HDMI, and you just expect a perfect, clean signal. But at the physical level, as that data is just screaming down the wire, something goes wrong. The signal starts to get really messy. What started out as this beautiful, pristine stream of ones and zeros gets all distorted and blurred by the real-world physics of the cable itself. Those sharp digital pulses turn into these garbled, wavy analog signals. It makes it incredibly hard for your devices to figure out what's a 1 and what's a 0. Okay, so the logical next thought is no big deal, right? If the data's corrupted, just let the super powerful processor in your computer or your phone sort it out. Use some clever code. It feels like a digital problem, so it should have a digital solution. But this is where the story takes a really fascinating twist. We're basically at a fork in the road here. We have two fundamental choices. Option 1, we can just let that ugly, distorted signal come into our device, digitize the whole mess, and then make our processor work overtime to clean it up with software. Or, option 2, we can fix the signal in the physical, analog world before it ever becomes digital data. And here's the kicker. It turns out that as we push data speeds higher and higher, we're talking tens of gigabits per second, that analog approach isn't just a neat alternative. It often becomes the only way to do it. Trying to digitally fix that kind of high-speed mess would just be way too slow and burn way too much power. The much smarter move is to fix reality first. And that brings us to the unsung hero of our story, the analog equalizer. This is a real, physical circuit that sits right there at the end of the cable. And its whole job is to intelligently reshape that distorted waveform to stretch it back into its proper shape. It restores the signal's integrity before it gets digitized, so the rest of the system sees a clean, crisp signal. It's literally an analog hero saving the digital day. So what is this foundational technology that makes everything possible? I mean, it creates our super powerful digital processors, but it also creates these incredibly clever analog circuits. Well, it all comes down to one revolutionary invention, CMOS. That stands for complementary metal oxide semiconductor transistors. Okay, you gotta love this. The basic idea for the transistors that run our entire world was actually patented way back in the 1930s, but it just sat there for decades. It wasn't until the early 60s that we could actually figure out how to build them reliably, but the real game changer, the thing that kicked off the entire modern electronics revolution, was in the mid-60s with CMOS. That's when we learned to pair two different types of transistors together, and that unlocked all the efficiency and scalability we depend on today. Now, this is where the story gets really mind-bending. The very same progress that makes our digital stuff smaller, faster, and more powerful, Moore's law, shrinking those transistors, it paradoxically creates a whole new world of pain for the analog designer. This creates a massive challenge. See, every time we shrink a transistor to make digital stuff faster, we actually degrade its analog performance. Its ability to cleanly amplify a signal, what engineers call voltage gain, it just drops. The transistors get noisier, less predictable. Old design tricks that used to work perfectly just don't apply anymore. So engineers are in this constant race, having to reinvent their methods just to keep up. So how in the world do you even tackle that much complexity? Well, engineers have to think in layers, kind of like wearing different hats. At the lowest level, you have to be a physicist, understanding the quantum mechanics of a single device. Then you zoom out and act like an electrician, figuring out how a few transistors work together. Then you become an architect, building those little groups into big functional blocks. And finally, you have to be a city planner, making sure the entire system works together. It's a lot. Okay, so hearing about all these insane challenges, you might be thinking, wow, analog design sounds like a dying art, a tiny little niche in our big digital world. But the reality is the complete opposite. Because it's so hard, skilled analog designers are more in demand than ever before. And look, you don't have to take my word for it. The data backs us up completely. If you look at the world's top circuits conference, the number of papers being published on analog design isn't shrinking. It's actually growing year after year. That's a huge signal that this field is buzzing with innovation and demand. And I think this quote really gets to the heart of it. This field isn't just about math and physics. It's this unique blend of art and science. It demands creative intuition, a feel for how a circuit is going to behave, and then backing that up with incredibly rigorous, precise analysis to prove that your gut feeling was right. So the next time you plug in a high-speed cable or fire up your smartphone, just take a second to remember that invisible artistry that's at work. Analog design is the craft of perfecting physical reality before it ever becomes data. And it's the critical and often totally overlooked foundation of pretty much all the technology that shapes our lives. And this whole thing points to a much bigger idea. Analog design is just one of these invisible worlds of engineering that power everything we use. It really makes you wonder, doesn't it? What other hidden systems, what other unsung heroes are working right now, just beneath the surface, making our modern lives possible?